So welcome to our last part of lecture 26. In the previous part, I just introduced the norm and orthogonality. So I just want to kind of put out some properties of these two definitions. First of all, the norm of a vector is 0 if and only if the vector v is 0. That's the only way that can happen. If you take a vector v and you scale it by a constant, so this could be a real or a complex number, then the norm of that vector is equal to the absolute value of the complex number times the norm of v. Okay, where, just so that you remember, that the norm of, or the length of a complex number is the square root of a squared plus b squared if lambda is equal to a plus bi. Okay, so if this had been a real number, if lambda had just been simply a real number, this is just the absolute value of the real number. And next, we say that u is orthogonal to itself if and only if u is the 0 vector. So the only vector orthogonal to itself is the 0 vector. And so another way of writing that is the inner product of u with itself is 0 if and only if u is equal to 0. None of these proofs are hard, and I recommend that you take a look at them in the textbook. Okay, because in the last little bit here, I want to show you that we've actually proved enough to kind of make we can state the Pythagorean theorem for any inner product space. Okay, and let me state the Pythagorean theorem. Suppose u and v are in V, and inner product space with u and v orthogonal. Then we have that the absolute, or the norm of u plus v squared is equal to the norm of u squared plus the norm of v squared. Okay, so this is not a way that you're used to thinking of the Pythagorean theorem, right? Because you're thinking Pythagoras had nothing to do with norms, and he didn't talk about vector spaces or anything like that. The point is, when you reduce everything to the special case of R2, and our inner product is the regular dot product, right? So the regular dot product, so this is equal to u1 v1 plus u2 v2. It does give us back the Pythagorean theorem that you want, or that you're used to, because you have a vector u. The norm of u is the length of this vector right here. Here's my vector v. Instead of drawing it at the origin, I've drawn it at the end of the vector u. So the length of this vector is the norm of v. And we're given that u and v are orthogonal. So that means that these angles, these two vectors are at right angles. And this vector right here, maybe I'll color it in blue. This is the vector u plus v, and its length is given by u plus v, the norm of u plus v. Okay, so this is stuff you would have learned in Math 1B03. So the Pythagorean theorem here says the length of this squared plus the length of this squared in a right angle triangle is equal to the length of the hypotenuse squared. But it turns out the Pythagorean theorem, like, it's nothing actually special about R2. It turned out the Pythagorean theorem is true because you're working in an inner product space, and inner products satisfy this relationship if the u and v are orthogonal. So let me give you a proof of this fact. So we're interested in the norm of u plus v, okay, squared. So according to the definition, that's just the inner product of u plus v comma u plus v, right? By squaring it, we get rid of the square root. Now we have homogeneity in the first coordinates and in the second coordinates, right? So let's do the second coordinate first. So this is equal to u plus v u plus u plus v v. That's kind of one of the properties that we proved about inner products. And then let's do it again. So this is equal to the inner product of u with itself plus the inner product of v and u plus the inner product of u and v plus the inner product of v and v. And these two things at the end, right, are equal to the norm of u squared and this is the norm of v squared. Yeah, the norm of v squared. Okay, but now we use our hypothesis that we know that u and v are orthogonal, but the inner product of u and v are 0. So 0, which is equal to uv, which is equal to the inner product of v and u, which is the complex conjugate, right? So we take the is equal to 0. So we have to have that the inner product of v and u is 0. So that means these two terms disappear. So at the end of the day, we get the inner product of u and v is equal to the inner product of u, the norm of u plus v squared is equal to the norm of u squared plus the norm of v squared. And that gives us our proof for the Pythagorean theorem. And the beautiful thing about this is that it works for any inner product space. So there's been a lot of kind of things that we learned today. We learned about inner products, we learned about inner product spaces, we learned about norm, and we learned about orthogonal. So keep in mind what you learned from Math 1B03 about these things. Whenever you see inner product, think of dot product, okay, as your example. The norm and orthogonality, these are kind of the same terms that we learned in Math 1B03. But we're trying to generalize it to more broadly to many vector spaces and many different types of functions that give us inner products. So that's it for lecture 26. Lecture 27 is really the next midterm. So I will see you again in lecture 28.